All right, well, this evening we're going to be starting the program in, in dental radiography. And this may be the most important thing that we teach you in the DATS program. Everything that we teach you is important. Infection control to numbering, etc. But radiology, I think, radiography or radiology is probably amongst the most important things that we deal with for a couple of reasons. Number one, without getting an X-ray license, you're not going to get a job. Because almost every ad, if you've already started to look on Craigslist, etc., almost every ad for dental assistants will say X-ray license or certification required. And that's not a negotiable issue. Some other things are negotiable, but as far as being able to take X-rays in an office is very important. This evening we're beginning the portion of our program with dental radiography or dental X-ray. And this part of the program may be the most important thing that we teach you during your 11 weeks of training. The reason it's most important, or amongst the most important thing, is that number one, without being X-ray certified, it's going to be very, very difficult to get a job. And so we're preparing you for the Dental System National Board called the DANBY. And at the conclusion of this program, when you get your certificate, assuming you're passing, and you all will, or I'll teach you. But on the completion of our program, you are then eligible to go online, and we'll teach you how to do this, and sign up to take the Dental System National Board called the DANBY. And that's a very comprehensive examination, but we're preparing you with 24 hours of training, both in the didactic or the book learning portion of it, as well as the practical part of it, which Lisa and the staff will be teaching you how to take X-rays, process them, mount them, etc. All the hands-on portion. But the examination for DANBY is mostly not the hands-on, because you're not demonstrating whether you can take X-rays. You're going to have to demonstrate that you know the material in the textbook. And unlike most of the other material that we teach in this 11-week program, you need to read the chapters of X-ray, of the dental radiography portion, starting with chapter 38 in your textbook, from cover to cover. You don't read bits and portions of it, because everything on the DANBY examination, including our examination, which you'll be taking, is fair game in that textbook. So starting for the next 3 weeks while you're in dental radiography, your reading assignment is going to get more involved and much more discrete. Any questions about that at this point? So the first reason X-ray is important is a practical point, that you're going to be, you need to be licensed in order to go out and get a position. The second part about it is that in X-ray, taking dental X-rays, you are working on your own. In most other procedures that you're working in a dental office, you're working alongside or beside the doctor or the hygienist, and you're assisting them in all the procedures. In dental X-ray, the doctor will come in and examine the patient and explain to the patient, you know, we need to take some X-rays, and generally the doctor will say we need to take a set of pictures, a set of X-rays. And from that point, the doctor leaves the room, and it's up to you to explain to the patient what we're doing, answer any questions about it, and then to perform these X-rays to the best of your abilities. So that at a point when I come back as the examining doctor, I can read the X-rays on the screen or on the computer, depending whether we're digital or we're still in film. So that's the second part of X-ray being very important, is that you're being left alone to do this, and you're expected to be able to do this on your own, quickly, efficiently, and very, very professionally. Number three, you're the first clinician in many offices to actually do something to the patient. The patient comes in and fills out a lot of paperwork, and then the doctor comes in and does a health review and a cursory examination of the patient, and then orders a set of pictures. Now, if I were to ask you all, what does a set of pictures in your mind, what does that really mean to you? Very quickly, give me an idea of when, if I said take a set of pictures on your friend next door, how many pictures do you think that would be?
5 or 6.
5 or 6, okay.
Yeah, I was going to say
You think 5 or 6? Okay, 5 or 6, anybody else? Anything else? Anyone else have anything dramatically? Well, a real set of pictures, a full mouth set of pictures, is 18 x-rays on a patient. And I'm sort of glad that tonight you're just getting into this, because you are at this point, don't know much more about radiology or radiography than the patients would. And so when the doctor says, Janie or Susie, take a set of pictures, the patient is also thinking 2, 4, 6 pictures. Almost no patients are thinking 18 individuals. And so if you don't inform them of what we're doing, we're really violating the patient's rights. It's called informed consent. And any procedure you do in medicine or dentistry, the patient has the right to understand all the ramifications, any danger issues, any consequences of whatever the procedure may be. So it's very important to you to understand that the patients will know just about what you knew at this moment, that they're thinking 2, 4, 6. Now, oddly enough, if you start taking a set of pictures and you're going toward taking 18, the patients don't stop you. Normally, they just let you go ahead. But at the very end of this, when you've taken 18 pictures, the patient will say, what was that all about? Why did you take so many pictures? I don't understand this. And you know what it is when you explain after you've done something to the patient? It's seen as making excuses and sort of covering their butt. And if you explain to them beforehand, it's called information. It's informing the patient. And it's a very critical issue that patients be informed and have the right to ask you questions about what you're doing and why you take so many, etc. And by the end of the radiology program, you will be very comfortable in explaining to them why we have to do this and what the values are, etc. Okay? Anyone have questions about that at this point? Okay, the next point is that because you are the first clinician to work on a patient, they judge how professional and how technically sound you are. So if you get in and take some x-rays and you seem to be fumbling and you're not very careful and you seem to hurt them and it seems to be a rough experience, the patients are beginning to see a picture of the office in its composite. And so by the time, as a doctor, I get to the patient, many times the patient is not very happy with their experience in the office. So clinically, many times you are the first to work on a patient. And the more professional you are and the more you're able to convey information and do this effectively, the more professional we as a group look together. And lastly, and probably most importantly, when you take a set of x-rays of patients, any number of x-rays of a patient, you are exposing them to radiation. And you are making a change in their body chemical, in their biological chemicals, in their microcosm that can never be erased. When we take an x-ray of a patient, we are making a very, very small change in the patient's body. And that leaves no room for making foolish mistakes. So if I've asked you to take a picture of number 6, and you're not thinking very clearly, and you take a picture of number 11, which is the canine on the other side, well, when I come as the doctor to check the x-rays and it's on the wrong side, the patient needs to be re-x-rayed, has to go through that experience, and the radiation effect, which we're going to cover in great detail tonight, what actually happens to the patient, that effect has to be repeated. And we have no right to abuse our authorization and the professional demeanor that we use. So it is very, very important that x-ray, like everything else in dentistry, be done very cautiously, but it does leave a remnant of radiation effect, which we will detail very quickly as we get into this evening. There is no delete button in the human body. So when we take an x-ray and if we mess up, you can't go back and delete as you would on a computer, erasing a misspelling. You also can't use an eraser, you can't use whiteout. The effect in the patient's body is there and it's there forever. I liken taking x-rays to the water bottles. You see the water coolers, that there's a bottle, a glass bottle full of water. and at the bottom you turn the spigot on and you fill your cup. Now, if we took a blue dye and we put 1 drop of blue dye into that water bottle, you would see no change in the water. You would smell nothing, you would taste nothing. 1 drop would appear to have done nothing to that bottle of water. If we took and put another drop in there, the same thing, and another drop. But at a certain point in time, when we drop that water, that drop of dye into the bottle, all of a sudden the water would discolor. And at that point we'd say, oh, that water is nasty, the water is no good, no one wants to drink it. But the effect of the water was from the first drop on, even though you didn't see what was happening. Now, when I entered dental school in the freshman year, I won't say how many years ago that was, it's a long way off. In my freshman year, the Department of they called it Radiography at that time, or Röntgenology. The instructor came to lecture us in the end of the first year, and he only had 2 fingers on his hand. These 3 fingers were missing. And all of us as students thought, my Lord, what type of dentist works with 2 fingers? Well, later on we got to know what the story was, and the story was that in the old days of radiography, we didn't know what the effects of X-ray, and many pioneers in using dental X-ray as well as medical X-ray were holding the film in the patient's mouth and moving the tube head around and exposing themselves to the same amount of radiation as the patient. No one thought much of it in the days because you didn't see anything, you didn't feel anything, you didn't taste anything. But many, many years after this instructor had started to take X-rays, and he was a pioneer in the early days of radiation, all of a sudden he woke up one morning and these 3 fingers had little abscesses on them. Turned out to be radiation necrosis. So all these years he had been absorbing radiation, and he saw nothing and felt nothing and seemed to be fine. Now today, obviously, we would never do anything like that, but in the early days, we didn't know what the effects of radiation were. And unfortunately, he lost the 3 fingers, and by my junior year, he expired or passed away from leukemia, which was most likely also from the radiation he was exposed to. Because back in the 1910s, 1920s, and 30s, we didn't use lead shields, because we were not aware of what X-ray was doing to the patients. We were also using much, much larger doses of radiation on the patients. Film was much slower, the processes were much less sophisticated as today. So that today radiation exposure is much, much smaller and less effect, but it is not negative. It is still there, and we need to always be careful for the health of our patients, and more importantly, the health of our staff. Because a patient is not going to be absorbing that many X-rays, etc., from a dentist. We, if we're not careful, can be, as health workers, could be exposed to it. And we'll talk later on this evening about the simple steps that we, as dental practitioners, need to follow so that we can be safe and not be concerned about radiation as part of our health. The dental system must have a thorough knowledge and understanding of the importance and use of dental radiographs. The system must understand the fundamental concepts of atomic and molecular structure and have a working knowledge of ionizing radiation and the properties of X-ray. These are big terms, and we're going to learn a whole lot more big terms tonight, but you need to begin to incorporate this. It would be better if you spend most of your time this evening listening to me and watching the screen than underlining in the book. Because if you get hung up with all the underlining and that type of thing, you can't write quickly enough to get all these notes together. And the big thing, our objective this evening is to make this understandable. Okay? This is a very difficult portion of the course, chapter 38 in particular, and so I would spend most of your time listening to me and watching the screen, but not bearing yourself into the textbook. Okay? Now, obviously you do whatever makes you comfortable, but the important thing is to understand this, not to get every note, because everything I say, except some of the stories I will tell you, are all in the book. Everything comes out of the textbook. Okay? So, Radiation used to produce dental radiographs has the ability to cause damage to all types of living tissues. This is the first time I'm going to say it tonight. By the end of the evening, I will have said it at least 3 or 4 times and elaborate on what that means, so that every time you take an x-ray, you have the ability to cause damage to all types of living tissues. Any exposure to radiation, no matter how small, has the potential to cause biologic changes to the operator, that's you and I, and the patient. The assistant must have a thorough understanding of the characteristics of radiation to minimize exposure to both to the patient and to the operators. You need to know more about taking an x-ray than you need, for example, to drive a car. All of us got here, most of us got here driving an automobile. And obviously, before you got your license, you had to take tests on the rules, etc. But you got your real licensure from driving the car. And indeed, we're going to teach you how to drive the car as well, meaning taking the x-rays effectively and positioning the cones. But you're going to need to know what goes on under the hood. And most of us have no idea in an automobile what goes on under the hood. And you don't really need to know that. But in x-ray, it's one step beyond just taking the pictures. You do need to know what you're doing to the patient when you take an x-ray. And so we're going to go into a great deal of detail on that as we go through the evening. Okay? Radiation was discovered by Wilhelm Conrad Röntgen in 1895. He discovered X-ray, and for many years it was called Röntgen rays or Röntgenology. During his lifetime, Röntgen was awarded the Nobel Peace Prize for Physics in 1901. In 1896, Dr. C. Edmund Kells was the first dentist to understand how important x-rays could be to us. And indeed, we started to use x-rays almost immediately after its discovery because we were able to see, by taking x-rays, what the effect of the pathology, the damage was in the mouth. We knew what a cavity looked like, we just couldn't see between the teeth or underneath the gum lines. And so it was pretty simple when we were taking x-rays, early x-rays of teeth and bones and gums, of what the decay or pathology was. And so we began to use x-rays on a routine basis as early as 1896, and it has continued ever since. Radiology has progressed from those early discoveries to the science that it is today. And we continue to improve our diagnostic abilities every single day. And now we're into digital radiography, where we're able to not use film, but to use digital computerization. We're able to send x-rays across the country, across the world. Virtually every day, as a dental director here, I get x-rays sent to me with a history of the patient's information, and they'll ask my opinion. What do you think, Dr. Becker? Is this a good case to do this? Is this appropriate to the treatment? Because we have we have 28 offices in this region, and I get x-rays and case information almost ever on a daily basis. And I'm able to give people my opinion by looking at the digital picture, whereas in years gone by, I would have to go all the way out to the office, wherever it was, and pull up the x-ray, and the patient wasn't still in the chair. So the modern techniques of digitalization has changed diagnosis and treatment, and also how quickly we're able to respond. So it is a marvel of technology that we're working with today. Okay. All things in this world are composed of energy and matter. Energy is defined as the ability to do work. So this projector and the light it is shining on the wall is energy. We can't grab it and put it in a bag. We can't conform it. We can't contain it. But it is doing a real job. And that's what's called energy. Matter is anything that occupies space and has form or shape. So the projector that's shooting the picture and the computer that's sitting on my desk here are both a sense of matter. They occupy space and they have form and they have shape. Okay? X-rays are a form of energy that can penetrate matter. So just like this projector is showing light on the screen, an X-ray wave is able to transmit through tissue and ultimately put a picture on a screen or on a piece of film or a digital plate. And so we have matter and we have energy. Okay, the basic building block of our world is called the atom. If we were to break down anything and everything in this room to its simplest form, that form, the simplest form, would be called an atom. How many of you have worked with or played with kids with a piece of Lego? Okay, well, pretty much all of you have worked with or played with Lego. What can you do with one piece of Lego?
Nothing.
Not very much. But imagine when you take one piece of Lego and you hook it together with another piece of Lego, we can build the world. In fact, I've been to demonstrations and things at the Smithsonian where they built the Eiffel Tower. They built all kinds of structures out of little simple pieces of Lego. Well, the Lego is like the atom. A single atom doesn't do much, but it is the building block for the rest of our world. And when atoms join together with other atoms, whether they're the same or not, they build the next building step, which is called a molecule. So we talked about water. Most of us know the expression for water as H2O. What does that mean? It means that there are three atoms, two of them which are hydrogen, hydrogen 1, hydrogen 2, and one atom of oxygen. And when you fuse those together, we get one molecule of water. Now water can take all three stages of matter that exist. The natural state of water is a liquid. But what happens when we put liquid on a stove and we boil the water?
Steam.
It heats up and it evaporates. Now, is it gone?
No.
Is it really gone? No, you can't see it anymore, but it is water vapor. And we can't destroy matter. We can only change its articulation. The same way we can take water and we put it into a freezer and it turn it into a rock. And all forms of matter can be changed, none of them as easily as water, but all of them can be changed. And we cannot destroy matter, we can only change its composition and its breakdown. Okay? The energy that holds the atoms together is called electron binding energy. Okay, as I said before, matter has many forms. It's composed of atoms grouped together in arrangements called molecules. And a molecule is the smallest particle of substance that retains the property of the original substance. The atom consists of two parts, a central nucleus and orbiting electrons. Now, what would you think is the most important factor for life on this earth for our existence as we exist today? What single thing do you think is the most important thing for a life to exist?
Oxygen?
Okay, oxygen is a good suggestion. Any other suggestions?
Water.
I'm sorry?
Water.
Water, that's important too. Anybody else? Well, the most important single thing is the sun. Our Earth is in an orbit around the sun, 93 million plus or minus miles away from the sun. And if something were to happen that would bombard our Earth, a huge collision from something in space, and we were pushed any further away from the sun than we are now, we would freeze immediately. Life as we understand it would be gone. Likewise, if we were pushed closer to the sun, we would burn up. So life as we understand it is predicated on our staying in the orbit that the Earth goes around the sun. Now, all the planets in our universe are going around the sun at their own orbits, and hopefully they stay in that position. And very few, if any of them, possibly Mars, would be acceptable for life as we know it on our Earth, because they're either too hot, too cold, etc. So life on our Earth is predicated primarily because of our relationship to the sun. Everybody understand that? Good. Now, the sun is like the nucleus of an atom. And I'll show you a picture of this in a second. And around it we have orbiting electrons, which are like the planets. An atom is identified by the composition of its nucleus and the arrangement of its orbiting electrons. At present, there are 105 different atoms existing. I leave this incorrect specifically. In 2005, that was correct. As of the last time I heard, about 6 months ago, Wall Street Journal said there were 118 atoms, each one individual. And we keep identifying new atoms all the time. Now, when I was a freshman in college taking freshman science, my professor got up there, very sophisticated gentleman, and he pontificated that at that time in 1957 that there were 88 atoms that had been identified by the scientists of this world. And he felt very comfortable that we had identified all the atoms there were. Now, I wrote down, as you students are doing, writing down 88, 105, whatever the number is, because I'm preparing for my test. But the fact is, it was an arrogant thing for him to say and a foolish thing for him to say, because we're never going to know everything about anything. And so we've gone from 88 to 118, and we will continue to identify atoms as we get more sophisticated, and we'll begin to identify everything in this earth better than we know today. But I don't think we're ever going to know everything about anything. It isn't meant to be. Okay. The arrangement within the atom is similar to that of the solar system, which I mentioned. The atom has a nucleus as its center or sun, and the electrons revolve around it like planets. Okay, the electrons remain stable in their orbit unless they're disturbed or moved. X-rays can disturb orbiting electrons. And that's the point we're going to talk about in great detail going forward. Okay? This is a graphic depiction of an oxygen atom. And as you see here, in the middle we have the nucleus depicted. Now in the nucleus we have plus particles, those are called protons. We have plus minus particles, and those are called neutrons. And the numbers of protons and neutrons and the electrons that go around them make up the individuality of that atom. No two atoms are identical. They each have a different composition. So we have in the middle, we have the nucleus, and this nucleus, which works like the sun, holds all these little particles called electrons, which are whirring around the nucleus of this oxygen atom. It holds them in place, just like the Earth is held in its place by the sun's gravitational pull. Now, what happens when we take an X-ray? Well, we bombard the tissues of the human being or whatever animal tissues that we're taking X-rays of, and that wave of energy, which is called an electromagnetic wave of energy, bombards through the tissue, and in dental X-rays it does nothing to the nucleus. Our X-rays are not strong enough to disturb or to concern the nucleus or the atom, the atom's central core. There are medical X-rays, however, that do bombard into the nucleus and blow up the nucleus. We use that for non-surgical procedures where we can't get with a knife, where we can't get in, for example, deep in the brain. And we're able to bombard today with very, very intense small particles of radiation of enormous magnitude that can bombard the atom and the molecule in the tissue and destroy the nucleus. But no matter how many times we take X-rays, dental X-rays of patients, there is no effect to the nucleus whatsoever. Now, what does happen is that when we bombard the nucleus and the atom, is that we push these little negative electrons off of their orbit. That wave of energy, called the electromagnetic wave, is strong enough to push them off of their wave, off of their orbit. And what happens after the wave of radiation has gone through the patient, these little particles scramble to come back to the orbit or the place that they were before. But they never go back to the exact same position. So it's as if I had my hands out like this. I have 2 hands, 10 fingers, and a huge wave of energy blew my hands apart. And when the wave of energy went away, my hands, which still had 2 hands and 10 fingers, came back together, but in a different configuration. Now this way I am unable to pick anything up. I still have 2 hands, 10 fingers, but it's not as functional as it was originally. And that's what we're doing when we take an X-ray of a patient. We are disturbing these little electrons and making them less functional as that they were before, changing their polarity from negative particles to neutral or positive particles, and they are never again exactly the same as they were before. Anybody have a question about this? Because this is the basic essential of what we're doing when we're taking an X-ray of a patient. Now this is minute. No one knows how many atoms, how many molecules, how many tissues we really affect with the dental X-ray. But we do know that it is a very tiny amount. But that does not give us the right to abuse that, because we can't see it and can't feel it and can't smell it. So that, and you need to know and understand that when we take a dental X-ray, we are making a change which is forever. It is tiny, but it is an irreversible change in that patient's tissues. And that goes back to the first statement I made. Any questions, issues? Okay. Now, you see if I move my hand in front of the light here, you see a shadow on the screen, right? Take it away, the shadow is gone. Put it back again, and you get the shadow again. Now, if I were to give one of you a camera, regular camera, to take a picture of the shadow, that after I took my hand away, the shadow would disappear from the screen, but you would have a photograph of the shadow as it was at that second. And you know, what do we call X-rays after they've been processed? We call them radiographs. And what do we call them when we're using a camera? A photograph. And what we're doing when we're taking an X-ray is we are photographing, we're capturing the movement of these electrons off of their orbit and the shadow that they create with their movement, just like my hand. And what we're doing is we're capturing the image on the film or on the screen from the motion of those electrons, which create the picture that we are able to create. Any questions? Okay. So this is the basic function. This is the basic breakdown, and we'll go into some more detail in a few moments. But this is what you do when you take an X-ray, every time. If you got an image, you made a change. These little electrons have been changed. All right? So repeating some of the material we've just spoken about, the nucleus or dense core or inner core of the atom is composed of particles known as protons, which are positive, and neutrons, which are neutral. Protons are positive electrical charges, and neutrons carry no electrical charge. Dental X-rays do not affect the tightly bound nucleus, but they do affect the electrons which are floating in space around the nucleus. Okay? Now, you will hear people say, oh, I had so many X-rays taken of me, I glow in the dark. Well, that's just an expression. When radiation, dental radiation goes through, or any diagnostic radiation is performed on a patient, the radiation effect, the electromagnetic wave of energy, goes right through the patient, comes out the other side. It leaves no residue of radiation. So you don't glow in the dark. There is no radiation in your body after you've been exposed. But what has happened is the radiation wave, which we just described, is pushing those electrons around. So the effect of the radiation is always there, but the radiation itself is never there. Now, there are procedures in medicine. For example, treating thyroid cancer, we use radioactive iodine. It's a special preparation of iodine that's injected into patients who have thyroid cancers. And that material does collect in the thyroid gland. It is very effective in helping to cure thyroid cancers. Those patients, when they're undergoing this, they have to be in special rooms that are lead lined, etc. And anyone who goes in to visit them, etc., and you don't have visitors during that period of time, they can be exposed to actual radiation. But that is very different than what we do when we take x-rays. Okay? So the therapeutic use of radiation is very different than the diagnostic use of radiation. Okay? These electrons, as I said, are very tiny negatively charged particles. They have very little mass. They orbit around the nucleus of the atom, and the orbital path of this electron is called an electron shell. As you noticed on oxygen, it had K and L pathways. Well, those are called electron shells. And every atom has its own number of byways. I sort of liken them to the beltway. You know, we have 495 going around Washington, and we have 695 going around Baltimore, and those are the circles that the cars go around the nucleus of the cities, etc. But the fact is that each atom has its own number of orbits, etc., and it's called an electron shell. Okay? The electrons remain stable in their orbit around the nucleus until X-ray photons collide with them. A photon, P-H-O-T-O-N, is a minute bundle of pure energy that has no weight or mass. And so we have a photon of energy coming off of this projector that is showing this. This is a photon of energy for light. We have photons of energy for television, radio, all the other electromagnetic waves of energy, which we'll describe in a few minutes. X-rays have enough energy to push the electrons out of their orbits, and they produce ions. So the electron then is called an ion. And the atom that gains or loses an electron becomes electrically unbalanced, and the process is called ionization. So the electrons become ions, the process is called ionization. And that is the process that we are disturbing in the human body or the animal, whoever we're taking x-rays. That ionization is the deficit or the defect that we create in a very, very small amount. Any questions about these? Okay, good, thank you. Okay. Ionization is the process which electrons are removed from their orbital shells of electrically stable through collisions with the X-ray photon. And these definitions are clear in your book. You want to go back and memorize some of these definitions when you're reading through your textbook. When an electron is removed from the atom, a new ion pair exists or results. The harmful ionizing effect of X-rays in humans can result in the disruption of cellular metabolism and can cause permanent damage to living cells and tissues. This is the second time I've told you basically the same thing. Now you should at this point beginning to get a better idea of what that means. I'm going to repeat it several times through the course of this evening. Any questions about that point at all? Okay, good. All right. Now, the same thing happens with a molecule. Here we have a molecule of water that's depicted. So we have one hydrogen atom, another hydrogen atom, and one oxygen atom right in the middle. And what's holding these atoms together are the electrons that are whirring around this molecule through this atom. And so when we bombard the molecule, this electron holding these together may move to here, and this one may move to here, and this one may move to there. And again, it is still a molecule of water, but it is a changed molecule of water. And the same thing as we grow more and more complex, from an atom to a molecule, to a tissue, to a system, to an entire body, all these are conglomerations of the basic atomic structure, getting more and more complicated as things are built from it. So the dental system must be familiar with the unique characteristic of X-rays. X-rays are a form of energy that can penetrate matter. Like visible light, radar, radio, and TV waves, they belong to a group called electromagnetic radiation. All of them are essentially the same. Electromagnetic radiation is made up of photons that travel through space at the speed of light in a straight line with a wave-like motion. Now, if you look at this picture on the screen, it talks about the dental X-ray, it talks about the sun, it talks about photography, it talks about microwaves, radar, television, and radio. Today we live in a world that everybody has television. Everybody seems to have cell phones. But when we go to push the button, or even using the remote, even more manually, how does a picture get in that television screen? How does that happen? You're all so young that you can't even imagine life without the TV. Well, I was 8.5 years old before the first television, I saw the first television picture. 8.5, I went 8 years without being able to watch television.
Why were you doing
It was a much better world then, because we read books, we listened to music, and we actually played and talked to each other, which today, unfortunately, kids are buried away from this. But anyway,
What do you do at night after work when you want to relax?
well, you might listen to music or listen to the radio or actually talk to your loved ones.
Oh, God.
Oh, God, right? Well, anyway, all of these are forms of electromagnetic radiation. What happens with the TV, just to simplify things, is that there's a wave of energy that is transmitted from the studio or from, and if you're talking about the direct TV, which is the easiest to see, a wave of energy comes from somewhere, whether it be the station or from a conglomerate of stations, and is shot up to a satellite that captures that electromagnetic wave of energy, turns it around, and shoots it back to your antenna. Now, in the early days of television, everyone had antennas that you could identify. And some of you might remember of seeing the antennas that used to be on the roof of houses, etc. And then we went to the rabbit ears, which some TVs still have, and again, all of you are too young to remember any of this. But the fact is, what we were doing is we were capturing that electromagnetic wave of energy by the antenna, which is exactly what DirecTV does, with its antenna which sits on the roof, and it brings it down into the building by way of a wire, which then ultimately ends up in the TV, which converts that electromagnetic wave into a picture and sound. It sounds impressive. It sounds like space age. It is. Mm-hmm. And again, before, going back in just my lifetime, we did not have any of these. Today we talk on a telephone and it sounds clear as a bell. I spoke to Makuda, who's one of our instructors, who happens to be in Senegal, Africa right now, and it sounds like she is next door. It's amazing. And I've called across, I was in China a couple of years ago and spoke to Scott from China, and it was like we were next door. And we're all taking this for granted, but these are electromagnetic waves of energy that have been cultivated and used for all of the things that go on today. Now, what differentiates all of these is their ability to penetrate through matter. Now, the sun is giving off electromagnetic waves of energy from the sun that travel all the way here, 93 million miles, and it actually travels much further than the Earth. It goes to others. But those electromagnetic waves, which are different than heat waves from the sun are what is keeping us alive, by keeping the temperature of our Earth in a hospitable temperature. However, we can go outside on a sunny day, which we have today, and you can take an umbrella and put it over top of your head, and what happens to the electromagnetic ray of the sun?
It's blocked.
It's blocked. We stand in the shade with nothing thicker or stronger than an umbrella with the thickness of nylon, not too much thicker than a couple of my hairs. And that's not very thick, as you can all see. And so we can block the electromagnetic waves of the sun with an umbrella. Whereas with an X-ray, the X-ray wave, which doesn't go nearly as far, only goes, in dentistry it goes 6 to 9 feet, in other X-ray we can go further, 30, 40, 50 feet, but the fact is an X-ray wave can go through a wall, and it can then go through your tissues and go through bone. The sun can't do that because of the nature of the wave that we have. The same thing is true with the microwave. We're all cooking or warming our food up with microwaves. And what do you see when you put a piece of food in the microwave and you look inside there? There's really nothing to see, is there? You hear a whirring sound, but that's the motor that's making the wave. And so basically, that wave is penetrating into your cup, going through the cup, and either defrosting or cooking your tea or your coffee or your frozen soup. And that microwave is stronger in the sense than the sun, which can't go through the cup. And the nature of that is the wave for the microwave is shorter than the wave for the sun, which is longer, and I'll show you a depiction of this in a moment. The strongest, or one of the strongest waves, are X-rays, because they can go through a wall, etc., and then they can go through tissue. So all of these waves are very similar, but they do different functions, and they're meant to be, applicable. Okay? The shorter the wavelength of all these waves, the greater its energy and its ability to penetrate through matter. Because of the high energy of short wavelengths, they are able to penetrate matter more easily than our longer wavelengths. X-rays have unique properties that make them especially useful in dentistry and medicine. Now this is what a wavelength graphically looks like. And we measure from the height of this curve, from here to here, that's the wavelength. That's the length of that wavelength. And now in the sun, that wavelength may be thousands of miles long. I'm sure some physicists could tell you exactly, but basically it is a very long wavelength. This, we'll say, is the microwave, so it's much shorter than the sun. And this one, which is very, very close together, this is called the X-ray, or it can be the micro or the short wave length as well. So the shortness of the wave dictates how the intensity of that wave going through matter. Now, the strength, how far it goes, has nothing to do with the shortness of the length, etc. So as I said, the sun can go 93 million plus miles and more, and the X-ray can only, the dental X-ray can only go 6 foot. But it can go through a wall or certainly through bone and tissue. Any question about this? Okay, good. Components of the dental X-ray machine. There are 3 parts of the X-ray machine, which you'll be covering in great detail later as you're going into taking X-rays. The tube head, the extension arm, and the control panel. And we'll cover these 3. The tube head we're going to talk about in great detail tonight. We're going to leave the other 2 for other chapters because we'll get into that. It's a different function, not nearly as complex. Okay? These are the pictures. You'll see it in your textbook of what a normal X-ray looks like. This is a digital X-ray machine, which many of us are using today. This is one for compact offices. This is called the panoramic or pantograph X-ray. And it takes all of the teeth and the jaws in one picture because it's a moving column that goes around the patient's body or head and gives us a very, very good gross picture of what's going on. But it's not nearly as discrete as the individual we call periapicals or bite wing X-rays that are used for differentiating caries or decay or periodontal disease. So this is another form, and you'll be shown this by your instructor as we go along in clinically. Okay? Now, we're going to talk about the components of the tube head. I'd like you all to turn your textbook to page 603. The outside casing of every tube head, X-ray tube head, is covered with a metal housing. The metal body of the tube head that houses the X-ray tube, and it's filled with insulating oil. And as you see graphically in your textbooks, the insulating oil surrounds the X-ray tube and prevents overheating by absorbing the heat produced by the X-rays. The tube head seal is made up of leaded glass or aluminum, and it seals the oil in the tube head. The X-ray tube is the heart of the X-ray generating unit. Inside, we also see the cathode and the anode. The cathode is, there are two cups that are inside of there. One is called the cathode cup, and the other is called the anode cup. The cathode cup consists of a tungsten filament made of molybdenum. A filament means a thin wire. So the cathode is made up of molybdenum and tungsten. The purpose of the cathode is to supply the electrons necessary to generate X-rays. That's where the X-rays are begun to be created. Electrons are generated in the X-ray tube at the cathode. Now, on a very, very hot day, you're riding down the road and you look ahead and you see what looks like a mirage. You can see it's like dancing little angels coming off the concrete. You've all experienced that at some point. And even walking in the street. It has to be very hot. But as you're riding or you're walking down, you see what appears to be a mirage of energy. Never seen it?
No.
Okay, well, you need to go on a hotter day. Anybody else not have seen that or experienced it?
Yes. Guys have seen dancing ladies?
Well, anyway, on a very hot day, the concrete is giving off, when it gets hot enough, is giving off waves of energy from the concrete which has been overheated. Okay? And in the tube head, the cathode is where, when it gets hot enough, it begins to boil just about, and it gives off electrons from the cathode itself, which are dancing, moving electrons in space that are given off because the cathode has gotten hot enough. Okay? The hotter the filament becomes, the more electrons are produced. Now the anode is the target for these electrons. Okay? The anode is composed of a tungsten target, a small block of tungsten that is embedded in a larger copper stem. And what the copper does, copper is an excellent conductor of hot and cold, and it wraps around the anode cup and helps to cool the electrons that are going from the cathode cup to the anode cup. You'll look in your picture and you'll see graphically how that works, okay? The copper around the target conducts the heat away from the target, thus reducing the wear and tear on the target cup. The purpose of the tungsten target is to serve as a focal spot and convert the bombarding electrons into X-ray photons. Photons being a wave of energy in a straight line, etc., and a minute wave of electromagnetic wave. Okay? The X-rays at the center of this beam are known as the central ray. Now, going back to the same picture you're looking at in the textbook, we have additional parts to the tube head. One is called the step-up transformer. Another is called the step-down transformer. And what they do, the electricity, when we push the button on the wall, is not hot enough to make the cathode hot enough to give off the electrons that we expect it to make. So when the electricity goes up the wall, across the ceiling, down the arm of the tube head, it enters into the step-up transformer, which heats that electricity tremendously hot. The same thing happens, we're sitting in a room now with fluorescent tubes. And if you came in here first thing tomorrow morning and turned the light on in this room, after having the light off all night, it will take a few seconds to a minute sometimes for the light to come on and get to be as bright as you would want it. You've probably experienced this at home when you come down to the kitchen or the bathroom, etc. Well, what's happening in that fluorescent tube is that there's a step-up transformer which takes that same electricity from the switch and magnifies the effect of the electricity so that in this tube, called the fluorescent tubes, it gets hotter and hotter till the glass tube that's in the fluorescent tube with the white powder called fluorescein dye glows in the dark. And that's what creates the light of a fluorescent tube. We're doing essentially the same thing inside the X-ray tube. We're heating up by the step-up transformer to get the cathode hot enough that it's giving off particles that would glow in the dark, if we were to look at it. Everybody follow that so far? You sure? Okay, good. Now, the anode collects that. Once those particles get hot enough, they go across, as I said before, they cross over from the cathode to the anode, where the copper wrapping of that cup cool it down enough for it then to be functional as in creating an X-ray wave. All right? Now, the next part of the inner tube is called the aluminum disc or the aluminum filter. How many of you cook pasta at home from scratch? In other words, not that you make your own noodles, but you take noodles, you put them in a pot and you boil them. Okay? Anybody do that?
Yeah.
Okay.
Come on,
Now,
guys.
after you boil the noodles, what do you do with the noodles after you've boiled them? You strain them, drain them. Do you wash them off with water?
Yeah.
Okay. Why do you do that?
So, because if you don't, they'll become sticky.
Okay. And what is that's the right answer? What is the sticky?
Starch.
Starch. Exactly. And what is starch? Sugar. Starch is pure sugar. And so you should wash your noodles off so that you eliminate the starch from the noodle. It reduces the caloric content of the noodle dramatically. Starch sitting on a noodle has no nutritional value. It has no nutrients, it has no minerals, it has no vitamins. It is pure and simple sugar. Now, sometimes students will say, well, I like to leave that on there because if it's a real thin sauce, it will stick to the noodle better. And that's a matter of taste. But the reason that we wash off the noodle is to get rid of the starch, which has no nutritional value. The aluminum filter, or the aluminum disc, does the exact same thing. When we're making the wave of the X-ray, that wave is made up of many components of waves of energy, some of which are not useful in making an X-ray picture, but they are harmful to the tissue. So the aluminum disc filters off the waves of energy that have been created that have no value for the X-ray but can be dangerous to us. And so it acts sort of like washing the starch off your noodle. We take the bad stuff off and leave the good stuff in. Okay? Now, after the wave of energy has gone through the aluminum disc and been scrubbed clean, it then goes through a lead collimator. A lead collimator takes a large or a wide range of energy and condenses it into a small point, a pinpoint. All electromagnetic waves of energy, whether it's the light or it's the sun or it's television, radio, they all start as very fine points of energy, and they immediately do this. They immediately spread their wings, so to speak. And that's why, at this point in time, if I put my hand in front of here, at this point, only this much of my hand is illuminated. Did you all see that here? Okay. Now what happens when I go back here? Look how much of my hand is illuminated. And if I go back here, and here, my entire body. And that's what every electromagnetic wave does. It starts small and spreads out like this, which is why we get a small picture here and a larger picture here. And the same thing is true of all the electromagnetic waves of energy. And we don't want to cover any more of the patient's body tissue than we have to that's covered with the film. And so we want to filter it through the lead collimator to keep it as narrow a beam as possible. So that's another important part. Then the wave of energy goes through the aluminum filter, through the lead collimator, and it comes out the positioning tube, which we call the position indicating device. And it's a rectangular or round tube which we place in the holder, which we'll be learning to do shortly, to focus, basically, just like we focus the picture coming out of a projector. Focusing it to take the picture of the tooth or teeth that we want to see and not the teeth that we're not interested in. And so that's the whole component that go inside the tube. So now let me explain to you how that we put this all together. So the first thing we're getting to do when a patient comes in is that the dental assistant informs the patient what we're going to do, how many x-rays the doctor has asked for, inform them of it, answered all their questions, and then proceed. Then we put a lead shield over the patient to protect the rest of their body, etc. And then we set up the x-ray machine and either the film or the digital sensors, however the thing is set up, and you proceed to go to take a picture. You place the sensor in the patient's mouth with the holder, and you run out of the room and you push the button. So when you push the button, the electricity, as I mentioned before, goes up the wall, goes across the ceiling, comes down the arm, and enters into the tube head. As it enters the tube head, it then goes to the step-up transformer, which makes that electricity much, much hotter. Hot enough that it makes the cathode begin to give off electrons of energy because of the excessive heat. When these electrons have gotten hot enough, they then jump across to the anode cup, which captures them and begins to cool them down. The wave of X-ray or photon of X-ray has been created here. It's cooled down here. And at a point when it is cooled sufficiently, that wave of energy drops through the aluminum filter, which scrubs off the harmful waves of energy, and then puts it through the lead collimator, which has it come out of the tube head in the smallest configuration through the position indicating device as possible. And that's the story of making x-rays. Anybody have any questions? Okay, let me tell it to you in one other way. I'm a tube head. Okay, picture me as a tube head hanging on the wall, all right? This hand is my cathode cup, okay? This hand is my anode cup. But in this hand, my cathode cup, I have a potato, an Idaho spud, all right? You push the button, electricity enters into my body, it gets very, very hot, and this potato starts to get so hot at a point where I can no longer handle the potato. I throw that potato over to this cup, which is called the anode cup, but this one has an oven lid on it. So I can hold that potato for a while because it's protected by the copper and with the oven. And after a period of time, when this has cooled the potato down enough, I drop the potato through the aluminum filter, which removes the skin and the bumps and the lumps and scrubs the potato perfectly clean and pristine. After being scrubbed by the aluminum filter, it then drops through the lead collimator, which cuts that potato into a long, fine point of French fry, which then comes out of the machine in the smallest configuration. And that's how this whole thing works. The position indicating device, the PID, is lined with lead and is placed against the patient's face during film exposure. The PID, which is the cone that we place next to the face, may be cylindrical or rectangular. The rectangular PID limits the size of the beams to that of a dental film. PIDs in dentistry are usually 8, 12, or 16 inches long. The length selected is determined by the X-ray technique being used. Generally, we're using more and more long cone. The long cone is considered to be 12 or 16 inches long. The 8 inches considered to be a short cone. Okay? The PID has a lead collimator which filters a stream of X-rays so that only those traveling parallel to a specific direction are allowed through. And so it filters the X-ray as well. The extension arm encloses the wire between the tube head and the control panel, and we'll cover that in much better detail when you're actually taking the X-rays. The control panel of an X-ray unit contains of three parts: a master switch, an exposure button, and the indicator light. The control devices, there are three things that we can control when taking an X-ray: the time, the milliamperage, which is called the MA, and the kilovoltage, which is the kV. And I'll explain those to you in a few moments of what they do. All right? A single centrally located control panel may be used to operate several tube heads. We have them pass through, as you see in this office, or those of you started to do your externship in here. You see that one tube head can go from one room to the other with one central focus. There are three types of radiation that we produce. It's really only one type, but it's how it works or functions in its place. Primary radiation is the X-rays that come from the target of the X-ray tube when they are produced. Using the discussion we previously talked about how X-ray waves are created, as it comes out of the tube head and through the PID, before it enters the patient's tissue, it is called primary. Secondary radiation is radiation that is created when the primary beam interacts with matter. So when that wave is in the patient's tissue, interacting and scrambling those ions or electrons that we talked about, that is called secondary radiation. And the third designation is scatter. Scatter is a form of secondary radiation. It results when an X-ray beam has been deflected from its path by the interaction with matter. X-rays in dental operations go through the patient's tissue and continue on for at least 6 feet. We generally suggest that the operator be 9 feet away from the tube head, because at 6 feet, almost all of the life of the electromagnetic wave is gone. But at 9 feet, all of the wave is gone. So it's not an accident that when you start to learn to take X-rays, you're going to cross over the hallway and push the button on the far wall of the operatory that you're working at, which automatically takes you at least 9 feet away. Now, the part that we as operators, as members of the team, are most concerned about for our benefit or our welfare is scatter. Scatter radiation occurs when the radiation has gone through the patient and is now floating in space, and if it's not directed properly, if you were standing in the direct line, could be affected by the radiation that could expose your bodies. And we don't allow that to happen. Some simple rules we'll talk about as we go a little further in this evening's discussion will tell you how safe you can be if you're not foolish about where you place yourself and the things that you do. So we have primary, secondary, and scatter. Visual characteristics that we're interested in are contrast, density, and image detail. These are the qualities necessary for a good radiograph. The dental system must understand how these variations influence the quality of the X-ray and can be adjusted from time to time. We use two basic terms in radiology. One is called radiolucent. Radiolucent structures allow X-rays to pass through them. The image of radiolucent structures appear dark or black on the radiograph. Air spaces, soft tissues of the body, dental pulp appear as radiolucent. The second differentiation is called radio-opaque. Radio-opaque structures do not allow X-rays to pass through them as well, and the image of radio-opaque structures appear to be white or light gray on the radiograph. Metal, enamel, dense areas of bone appear as radio-opaque. Now, this is what we're looking at is one bite wing radiograph. The bite wing radiograph is used primarily to determine or to define caries or decay. The individual x-rays, which we call periapicals, of which there are up to 18 of them, take each individual tooth and x-ray it from, shows a picture, an image of it from the very top of the tooth to the very bottom of the tooth, called the apex. Now, when you look at this picture, this bite wing, you see these bright white images of things on the tooth. Those bright white images are called radio-opaque. And what they are silver or gold fillings or restorations. And because the x-ray doesn't go through it nearly as well as it goes through softer tissue, it appears as we call radio-opaque. Now, if you look here, you see that the outer covering of this tooth, of every tooth, the portion of the crown, the outer covering is called enamel, right? And enamel is also radio-opaque, but it's not nearly as opaque as metal. And underneath enamel, we have dentin. And dentin is also radio-opaque, but less opaque than enamel. Again, the density of the material will determine whether it's opaque or radiolucent. Now, in the middle of every tooth, we have the pulp chamber. And you see this dark area in the middle of this tooth. It is dark and it is defined. What's in the pulp chamber of every tooth? You have nerves, you have arteries, you have veins. They are all soft tissue, correct? And so those tissues which are soft tissue appear to be radiolucent. Okay? So the pulp of the tooth is shown as radiolucent normally. Okay? Now, can you all see this area that I'm defining with my finger here? This dark area called radiolucent. What do you think that is?
Decay.
It's decay. It's decay. And why is decay radiolucent? Because what decay has happened is the softening and the breaking down of the hard substance of a tooth by the process of decay, the bacteria creating acids, using sugar as their substrate, and they eat away and break down the tissue with the acid, so it becomes softened, etc. And it appears, the decay on an x-ray appears to be radiolucent. Now this area on this tooth, I wouldn't need an x-ray to describe that if I were looking in the patient's mouth. That's a very big cavity, and indeed I could see that with my visual eye. I wouldn't need an x-ray. But if you look underneath this filling right here, this restoration, can you see the dark shadow underneath a little bit? Well, that is also decay. That is decay underneath the restoration. We call it recurrent caries or recurrent cavity. And it is decay that has worked its way under a restoration. Now, it could be that the original filling or restoration was not placed properly, or it could also be, and we look at this patient's mouth with so many cavities and so much decay history, that this patient didn't brush or floss this area very well. And indeed, the junction between the silver or gold filling and the tooth has broken down, and you get recurrent caries. Now, in this case, this is a small cavity. It's under the silver. I would not see this with my visible eye in the patient's mouth examining them, and most likely wouldn't feel it with my explorer, etc. But if I left this tooth undiagnosed and left it alone, it wouldn't take long before this would look like this. And that's the reason we take x-rays, to detect pathology, which includes cavities, cysts, tumors, etc., before they become overwhelming. And so if we catch this one at this point, we can save this tooth and restore it very comfortably. This one is going to cause a big problem because it is so large already. And this one, if you see this large dark area in the middle of this tooth, this is also decay under a filling. that I wouldn't see in the mouth either, because it's managed to get underneath the restoration. This tooth is about to have a root canal or an extraction. That cavity is so big. And so we want to catch decay at this point, not at this point, and not at this point. We also want to catch tumors and cysts and missing teeth and all the things that we're looking for in the human body long before they cause the problem that makes it obvious that they're there. So, everybody got that? Okay, so we have radiolucent, the pulp, radiolucent caries, radiopaque, silver and gold, and also the enamel and the dentin. Now, anybody guess what this is down below here?
The gums.
Well, would it be gum? Gum is all soft tissue, isn't it? That is the bone that's underneath the gum. The gum is covering the bone and covering part of the tooth, and you don't see it because it is radiolucent. Correct? So we have the bone, which is described as being radio-opaque as well. All right? Now, if I had, the process of decay is not exactly the way I'm going to describe it, but it's very similar. If I had an apple, and I dropped the apple on the floor, okay, and I picked the apple up, and I looked at it and said, well, it looks okay, and I put it on the table, and I don't do anything about it. In a day or two, I come back to eat the apple, and what would the area of the apple that hit the floor, what would that look like, and what would we call it? I'm sorry?
Dropped it.
Well, I dropped, but what would the apple? What would you call the apple, the part that hit the ground? How about bruising? Have you all heard that expression? Bruising a piece of fruit? It softens the fruit, right? Now, if I pick the apple up before it got too bad, and I cut the bruised or decayed, broken down, and bruising is really breaking down of the hard substance of the apple. It's been damaged, and it continues to decay and fall and become softened. If I cut the apple, that part of the apple that had been bruised or breaking down, and I wrapped it up with saran wrap and I put it in a refrigerator, I could come back in a day or two or three and eat the rest of the apple and it would be fine. Okay? The same thing happens with decay in a tooth. If we catch it early on and we cut off the decayed portion, we remove it, and we seal it off with a filling, restoration, crown, etc., that tooth can continue to function for a long period of time, if not forever. And so the process of breaking down is the same in a tooth as it is in the apple. Slightly different mechanics, but that's what happens. Okay? Now, one other thing to point out to you. Can you all see this black line right along the root of that tooth? Everybody see it?
Yeah.
Okay. What do you think if that's a black line? So is it hard tissue or soft tissue?
Soft.
It's soft tissue. So what's attached to the root of the tooth that's soft tissue around every tooth? Periodontal ligament. Periodontal ligament are those little fine fibers that attach a tooth by its root into the bony socket to keep it in its place. And so when we're diagnosing, not with bite wings, but with regular things, we're very careful to look at the periodontal ligament space, which should be continuous around every tooth. And so from one simple x-ray, we see all different kinds of things happening. The ideal contrast of a film clearly shows the radio-opaque white of a metal restoration, the radiolucent black of air, and the many shades of gray between. The reason I get the big bucks for examining x-rays is reading the shades of gray. Because there's very little that's all black and very little that's all white. It's the shades of gray in between that determine whether this is pathology, is this a cyst, is it a tumor, is it a developing abscess, etc. And that's what we are looking for, is all those different shades of gray. And the better the picture is, the more defining of the shades of gray, the better we can determine what's going on in the patient's mouth and body. Okay? The higher the kilovoltage, and kilovoltage is sort of like how strong the wave is. I liken it to gas. We talk about high test gas and low test gas. Well, high test gas has more oomph. It has more explosive power. Well, kilovoltage is the, not explosive, but it's the strength of the wave that's entering into the patient's tissue. The higher the kilovoltage produces more penetrating X-rays, but it gives us lower contrast. And so, opposite of what one would think, we want to use the lower wave of that energy called the 70 kVp rather than the 90 kVp. Right? A 90 kVp setting requires less exposure time and produces an X-ray that has low contrast, which makes it very hard to read. Okay? A 70 requires a slightly longer exposure, but gives us less shades of gray, which makes it easier to read the X-ray. Turn the light off again, please. Okay? Now this is called a step wedge. And what this is a cube of material that's been impregnated so that we can take an X-ray of it. And this picture is showing a step wedge that has been irradiated with a 70 kVp. So you see very dark on one side, and you see very light on the other side. Now keep this image in mind when I switch to the next picture, which is the 90 kVp. And you can see here that there are so many more shades of gray. And it's almost impossible to tell this one from this one, and this one from this one, and this one from this one. And so, although it gets you more shades, they are very hard to interpret. So that the 70 kVp is what we're hoping to use in dentistry on almost every patient. In the old days of radiography, we were able to change the settings on the X-ray machines, and the technician or the dental system was expected to do so. Today, most of them are preset, and so whenever possible, we're using 70s. Okay? Density is the overall blackness or darkness of a film. Okay? A radiograph with the correct density enables us to view the black areas, like the air spaces, and the white areas, the enamel, dent, and the bone, and all the gray areas in between. Now we gave you all uniforms that are dark blue with white writing. And that's not an accident. If you buy any apparel that has a logo on it, it generally has either a light background with a dark logo or printing, or a dark background with a light one, because you want to show off, and the manufacturer wants you to show off the logo as well. And so if you buy one of those caps with the swoosh on it, the Michael Jordan, caps, indeed, they're always very contrasting. And the reason for that is people can see the logo. And you can be proud of what you spent too much money for. And people can identify with what that logo is. Okay? The degree of density is controlled by the MAS, which is called the milliampere seconds. We call them the MAs. And that setting, we have KVPs, we have MAs, and we have time. Those are the three factors that we can control in taking an X-ray. And less do you have much control over it. It's the modern X-ray machines, it's all being done electronically. But those are the three factors that give you a better quality picture with the proper settings. Any questions about these three? Okay. Other factors influencing density, the distance from the X-ray tube to the patient. If you don't get it close enough to the patient, you're going to get a lighter or less dense image, which again will be very difficult to define. The developing time and temperature can also affect the density. If you're using film and you're not in the digital world, the processing time is, if it's too long and the temperature is too high, will be too dark, and if it's too short and the temperature is low, the film will be lighter and very hard to define. The body size of the patient makes some determination, and so we need to adjust for very heavy heavy bone people sometime in order to get the right density of the picture on that patient. There are 3 geometric characteristics that affect the quality of the X-ray. These are sharpness, magnification, and distortion. So obviously we want the picture to be as sharp as possible. We want the picture to show on the X-ray film the exact size of the tooth in the mouth. We managed to figure this out that using the long cone paralleling technique of taking X-rays, which is what you'll be learning in the coming days and weeks. This will give you, if you set the tube head and everything up appropriately and take it in the right terminology and direction, the image on the film or the sensor will be almost the length of the image of the actual tooth in the mouth. And we're able to do root canals by putting files into the tooth, etc., and being able to see how long the tooth actually is by using the X-ray in a file. Sharpness refers to how well the X-ray reproduces the fine details of an object, and obviously you want it to be as sharp as possible. Sharpness is sometimes referred to as detail, resolution, or definition. The sharpness of an image is influenced by focal spot size, film composition, and movement. If we're taking a picture of a patient in a particular tube, we want to focus in on what we're looking for. So if we're taking an X-ray of the molar, we want that molar to be the focus of where we're taking the X-ray. We're not interested in the bicuspid or the second molar. The film composition means that we want to compose the picture so we see exactly what we're interested in. And obviously, there should be no movement of the patient or of the tube head, because any movement will give a distortion to the image on the screen. Any questions so far what we're talking about? Good. Radiation safety. Now I'm going back, this is the 3rd time, I think, maybe the 4th time I'm saying this. All ionizing radiations are harmful and produce biologic changes in living tissue. Now, what is the biologic changes in living tissue? Somebody give me an answer. Anybody? What did we talk about? The ions, the little electrons on the patients in the atom being displaced. That's what I'm talking about. When those atoms, when the atom is affected, etc., by being bombarded by the electromagnetic wave of X-ray, it pushes those little electrons off of their space, as we said, and when they come back, they are never in the same position that they were before. So we have biologic changes in living tissue every time we take an X-ray. It is minute, but it does occur. And that's when we're talking about ionizing radiation, because the procedure is called ionization, if you recall from earlier in this lecture. Anybody question this? Okay. The amount of X-radiation used in dental X-ray is small, but biologic changes do occur. If you got a picture, if you were able to obtain an X-ray picture, then some changes occurred in that patient. That's what caused the image to occur on the film. And so the assistant must understand how the harmful effects of radiation occur and how to discuss this with your patients. Because when they ask you questions, you need to be informed, you need to inform them, you need to tell them what we're doing and what we're going to do, and you need to minimize in their minds what it is, but not to eliminate it. They have the right to understand that when we take an X-ray, we are making a change. It is minute. It is a tiny drop of blue dye, going back to my first story. One drop of dye in the bottle doesn't ruin the water, but enough drops of dye will. And just like with my instructor, he was radiated so many times that he ultimately lost his fingers and then his leg. That's an extreme that doesn't occur today. But that the fact that we've minimized it does not mean that we can forget that we are making changes in people's bodies every time we take an X-ray. So, everybody clear on this changes that are occurring? The biologic changes every time we take the picture. Okay? Ionization, as I said, is the harmful effect of X-rays in humans that can result in a disruption of cellular metabolism and cause permanent damage to living cells and tissues. You need to memorize these definitions, and not only memorize it, but know what they mean. That's more important. Ionization is the process in which electrons are removed from electrically stable atoms through collisions with the X-ray photons. The atoms that lose electrons become positive ions as such, and they are unstable. They are incapable of interacting with and reacting with other atoms, tissues, and chemicals. So they are very, very small amounts of them are affected. But every time we take a picture, ionization is what creates the picture. And it does affect the tissues of the human body. Well, any tissue. Okay. Exposure to radiation can bring about changes in body chemicals, cells, tissues, and organs. The effects of radiation may not become evident for many years after the time the X-rays were absorbed. This time lag is called the latent period, L-A-T-E-N-T. So with my instructor, he took X-rays year after year after year and saw no effect. At the time that he finally saw the effect, that was too late, obviously, and that period of time between not seeing it and actually of seeing the effect of it is called the latent period. Anybody have a question about that definition? The latent period is the time that now, we had this when we dropped a bomb on Nagasaki and Hiroshima in 1945 to end World War II. We killed many, many thousands of Japanese people. It was estimated that 80 to 100,000 Japanese people in those two cities were killed almost instantly. But hundreds of thousands of Japanese people were affected by the residual radiation that was left in the Japanese cities, and many of those effects were not seen for days, weeks, months, and years later. That is called the latent effect. And just recently we had a meltdown in Japan, unfortunately, when the tsunami ruptured the power plant, and radiation spilled out into the atmosphere approximately 3 years ago. You all remember those stories? Mm-hmm. Right. And only a couple thousand people died at that point from radiation. Many of them died from drowning because of the tsunami, but only a couple thousand were identified as having been killed by radiation. But in the coming days, weeks, months, and years, many thousands of Japanese people who lived on that coast are going to show signs of radiation that will not be apparent until the latent effect comes into account. So the fact that you can't see it doesn't mean that it doesn't exist. Exposure to radiation has a cumulative effect over a lifetime. When tissues are exposed to X-rays, some damage occurs. Tissues have the capacity to repair some of the damage. However, the tissues never return to their original state. The cumulative effect of radiation exposure can be compared with the cumulative effect from repeated exposure over the years to the rays of the sun. Today, what do you think is the fastest growing percentage of cancer tumors in the Western Hemisphere?
Oh, no.
Skin cancer.
It's skin. Skin cancers were, not that they were unheard of, but when I was in dental school from 1961 to 1965, they would take us on rounds across the street to the hospital. And we would see different disease processes, and when you saw the effects of a disease, you never forgot it. It was a wonderful experience, and it's a great teaching tool that all medicine and dentistry uses. I never saw a real skin cancer in those 4 years. I saw pictures, but I never saw a patient with a real skin cancer. I can assure you that I can take you right up the street here to the Howard County Hospital and find many patients on the wards or certainly in the clinics with skin cancers. Skin cancer today is absolutely phenomenal. It's exploding. And it was estimated in 2012 that there were more skin cancers diagnosed and treated than all the other cancers combined. That's pretty astounding, isn't it? Much more than breast and much more than prostate and much more than all the others. Skin cancer is occurring every day. Anybody have an idea why you think there's skin cancer so much more today?
Because people are not applying their sunscreen.
Well,
Is it
that's
because
true.
So
Those
many
are the-
sunlight?
Well, there are several factors involved. Some people don't use sunscreen. Now, I have had 3 skin cancers, so I don't go anywhere without coating myself. I was down the beach this weekend, and I used 50. I'm not sure that 50 is any better than 30, but certainly nothing below 30 should be used if you are sensitive to skin. And indeed, you want to protect your skin whenever possible. So when I go out in the skin now, I wear a big floppy hat, and I coat myself with 30 or 50, and I try to stay out of the effects of the sun the best I can. Because I've already had 3 skin cancers, one of which was a melanoma. That's the kind that kills people. I was very fortunate; they caught it early enough, and I've gotten along very well. But the effect of the sun today is so much more dramatic than it was in the past. Years gone by, people didn't get skin cancer, but none of them used sunblock, and people used to go out and get sunburned almost every weekend,
Yeah.
never thinking about the blistering,
That's
etc.
me, I'm from an island.
Mhm.
I don't use sunblock.
Okay, well, you should start to, because
I do.
even people of color can now get get sunburn, they can get skin cancer. The fact of your having melanin, which gives you the color, those of you who are people of color, that is a protective element in your skin. But it no longer guarantees you that you can't get sunburn and skin cancer. So all of us should be protecting ourselves. And more importantly than protecting yourself, you need to protect your children.
Yeah, I
Today,
trust my daughter.
if you take your child out in the sun and allow that child to get sunburned badly enough that they blister, and that you might have to take them to a doctor or a hospital or one of the walk-in clinics, when a doctor sees you, a physician sees you with a child with that magnitude, because a blister is a 3rd-degree burn of the skin. And whereas we used to sort of laugh that away years ago, today if you take a child into a hospital or a medical clinic, they will write you up for this child, etc. And the doctor will give you a stern lecture about not allowing that to happen again for your child or any other children. And if you come back to the hospital with a second child or the same child with recurrent burns again, the next person you're going to speak to is Child Protective Agency. They can take your child away. That is considered to be abuse. This is nothing to laugh about or to be quizzical. This is reality today. Because once a child has been burned once, they are susceptible the rest of their life, because it is a cumulative effect to their skin, just like it is to yours and mine. And that's where the sunburn is very similar to radiation. The effect of it from the very beginning is there for an eternity. Anybody have a question about this? So you need to be very careful for yourself and more careful with your children. And why do we think that we're getting more sunburn today? Well, many people think it's because of the ozone layer that covers our atmosphere. You've all heard the expression, the ozone layer? Well, ozone is 3 atoms of oxygen, O3. And it acts as a blanket over our atmosphere, and it deflects some of the rays of the sun off of our atmosphere from coming to the surface and causing the damage that it does. Today, there are large gaping holes in the ozone layer, and most of this is attributed to the pollution that we're putting out from our automobiles, from our coal burning furnaces where we make electricity, etc., etc. Now, there's not direct proof of this, but it seems so obvious to most people. The carbon dioxide given off and the global warming is a real fact. And the fact is that today we're finding skin cancer to be absolutely epidemic in the Western Hemisphere. We have acute and we have chronic radiation exposure. Acute radiation exposure occurs when a large dose of radiation is absorbed in a short period of time, such as in a nuclear accident. So when the people in Japan recently, 3 years ago, were inundated with radiation, that was an acute exposure of radiation to those people. Chronic radiation exposure occurs when small amounts of radiation are absorbed repeatedly over a long period of time, which is also happening in Japan right now, because radiation permeated their soil, it permeated their homes, the water, etc. of their homes. And they are getting small amounts of radiation, those that live close enough to the target area, etc. Chronic over a long period of time. It may be years after the original exposure that the effects of chronic radiation exposure are observed. Just like my instructor. He had small doses of radiation, saw nothing, no effect of it. It was chronic radiation exposure. Only when his fingers began to abscess did he realize what the problem was. Okay? Radiation can cause genetic and somatic effects. X-rays affect both genetic and somatic cells. Genetic cells are the reproductive cells that we all have. So for men, they are the sperm, and for women, it's the ova, etc. Damage to genetic cells is passed on to the next generation. These changes are referred to as genetic mutations. All other cells in the body are called somatic cells. Soma meaning body, okay? X-rays can damage somatic tissue, but the damage is not passed on to future generations. So although I have had 3 skin cancers, certainly not going to have any more children at this point, but even if I did, most likely the radiation that I absorbed that helped create the cancers that developed, some of it's genetic, but a lot of it was exposure to sun, is not going to be passed on to my succeeding generations. However, if you were exposed to large doses of radiation, like the people in Japan along the coast, some of them, their reproductive organs would have been affected. And those genetic effects will be passed to their next generation. Okay? Now, here we show a dog. Let's call it a Labrador Retriever on the top. And this Labrador has been exposed to radiation from some source of radiation. On the right-hand side, this dog, which was perfectly healthy before it was exposed, appears to be very sick and, broken down and not very healthy if you look at the dog on the right hand of our picture. That dog, however, if it was a female, can give birth to a puppy that appears to be perfectly normal. So in this case, this dog had a somatic mutation which affected her tissue, but it did not affect her puppies or her babies. On the other hand, we have a Labrador standing right next to the same dog exposed to radiation, and in this case, the dog appears perfectly fine. No effect that you can see. But that dog could give birth to a puppy that had genetic malformations. And we see this. We saw it after World War II, we see it when radiation explosions, and we're going to see it, unfortunately, in Japan. As I said, we saw a couple thousand people that died, we saw people that are going to develop leukemias and skin cancers, etc. Hopefully, not many of them will have been affected through their genetic organs, their ovaries and their sperm, but the fact that they're going to give birth to children with all different types of defects. Now, everybody understand the difference between somatic and genetic? Very, very important point. Okay? The following organs are considered critical organs, which means that they are most sensitive to radiation: skin, thyroid, lens of the eye, and bone marrow. Skin, particularly, and bone marrow, they're affected so much by radiation because these are cells that reproduce themselves so quickly. If we cut our hand or cut anywhere in our skin, we put a little Band-Aid on there, and within days, the skin has fused together and healed itself. However, if we cut through the skin and we actually cut into the muscle underlying it, that muscle cell grows very slowly and hardly at all. When we work out, we are not growing more muscle, we're making those muscle cells bigger and stronger. We are not creating more of them. And so, if you cut your hand and your skin grows back and the muscle was cut, most likely the physician is going to have to suture or tie the muscle tissues together to get it to heal. And so, skin, thyroid, lens of the eye, and bone marrow are tissues that reproduce themselves very quickly and are more susceptible to radiation changes. Maximum permissible dosage. The maximum permissible dosage, MPD, of whole body radiation for those who are occupationally exposed. Now, who would that be? Who's occupationally exposed? Us. Right, you're working around radiation. The government says that those of us that work around radiation can be exposed to 5,000 millirems or 5.0 rems of radiation per year. The government says this amount of radiation to the whole body produces very little chance of injury. What are the two most important words on that screen? Very little. Very little is not none. Very little is very little. So for non-occupationally exposed persons, the current MPD is 500 millirems or 5 millisieverts per year. We in dentistry we strive for an occupational dosage of 0, which means that if you are exposed to no radiation, you have no chance of absorbing radiation if you weren't exposed to it. And by following the simple rules that we'll talk about a little bit later and in the coming days of this class, you do not have to be concerned about radiation working in a dental office as long as you are following the basic rules and not being foolish and violating them. So 5.0 rems is a tiny, tiny fleck of radiation, but 0 is better than 5. And that's what we strive to affect and to achieve in dentistry. And I'm sure they do in medicine as well. Radiation risk and benefits. Background radiation comes from natural sources such as radioactive materials in the ground and cosmic radiation from space. We can't avoid that. Exposure from medical or dental sources is an additional radiation risk, and we want to minimize that the best we can. Okay? Now, when dental x-rays are prescribed and exposed, the benefit of the disease detection far outweighs the risk of biologic damage from receiving small doses of radiation. But we do not take x-rays just because we can, and we don't take x-rays just because we can extract a fee from the patient or the insurance company. The whole point of taking x-rays, as I showed on that one x-ray picture, is to detect disease, pathology, at its earliest state so that we can minimize it, prevent it, and treat it effectively. And so the advantages of taking x-rays, both in medicine and dentistry, far outweigh the radiation exposure that we expose patients to. But that doesn't give us the right to violate this and take pictures we don't need. Nor does it give us the right to take pictures that are not comprehensive. And the picture needs to be diagnostic. That's the end result. Diagnostic means that the doctor needs to see everything he needs to see in that picture. There is no such thing as a perfect x-ray. What the x-ray needs to be is diagnostic, so that I as a clinician can look at a picture and feel very comfortable that I have seen all that I need to see in and around that tooth to assure the patient that what we see is fine. And that risk is well worth the risk of taking some x-ray pictures. But it does not allow us to violate the principles of minimizing it. Any question about that issue? Okay, moving forward. Okay. The responsibility of the dentist is to prescribe x-rays only for diagnostic purposes, to ensure that all the equipment is properly installed and maintained in a safe condition, to provide appropriate shielding to protect the staff and the patients from the effects of radiation, to require that anyone exposing radiation be properly trained and appropriately supervised, to obey all state radiographic licensing requirements, rules, and regulations. Every state in America has a rule and a regulation about taking x-rays. 40 of the states in America, roughly 40, sometimes a little less, sometimes a little more, but 40 states accept the Dental Assistant National Board. That's what we're preparing you to take. They respect that and accept it as the licensing credential for dental personnel to take x-rays. The other 10 states, some of them have their own testing procedures. Some of them accept the DANBI, but if you didn't take the DANBI, you need to take their examination and testing.
So I should call Bermuda.
Yes, you should check with Bermuda, because I have no idea in Bermuda what the licensing
Right.
credentials are. Okay? And lastly, to participate in obtaining informed consent. As I said to you in the beginning, the doctor is not going to stand there and explain the procedures to the patient. We're going to abrogate or pass that along to you guys, the dental assistants, to explain to the patient informed consent, telling them what the risks are, what the values are, answering their questions. But ultimately, as the doctor and being the licensed person in the practice, I'm responsible. So my job is to participate in it, but not really to do the procedure called informed consent. Patient protection. A lead apron and thyroid collar must be used on all patients for all exposures. This rule applies to all patients regardless of the patient's age or sex or the number of films being exposed. The lead apron should cover the patient from the neck and extend over the lap area to protect the reproductive and blood-forming tissues from scattered radiation. Okay? Many states mandate the use of a lead apron, and almost all of them do today. Now, a couple of years ago, here in this Columbia office that we're currently sitting in, I was sitting in my office and a young hygienist came out of her room. She was getting ready to treat a patient, and she was fresh out of school. She came into the room and she was visibly upset. And I said, what's the matter? What's the problem? She said, well, this elderly gentleman won't let me put the lead shield on him. He says it's not necessary for him. So I said to her, sort of annoyed because she'd already wasted 10 or 15 minutes of the appointment for the cleaning, you need to go back and tell this elderly gentleman that this is a requirement not only of us but of the state, and he needs to wear the lead shield. So she went back to her room, and about 5 or 10 minutes later she comes back again, and now she's all blotchy and red, and she's really upset. And I'm getting very upset because now 20 minutes of a 45-minute appointment has been wasted. And I said, what is going on now? He doesn't think it's necessary, he doesn't want it. He was being ignorant. Anyway, at this point I get up from my chair in my office and I follow her to her chair. And the first thing I do is I pick up the patient's charts, the chart editing, and I look at his name so I can address him appropriately. I also look at his date of birth. Now why do I look at his date of birth? Well, she called him an elderly gentleman. And I said, I'm wondering what does that mean to her? And now I'm really, really steamed, because this elderly gentleman is 10 years younger than me. So you can imagine how I'm now really upset over the radiation and the wisdom, but also she must think that I am a fossil. He's an elderly gentleman. Anyway, I come across and I speak to the gentleman. I say, sir, what seems to be the problem here? You've wasted such valuable time. What is the big issue about not putting the lead shield on? And he says, oh, I'm not going to have any more babies. I said, well, that's probably a good thing. But do you think that lead shield is only protecting your reproductive organs? What about your heart? What about your kidneys? What about your lung, your pancreas, etc., etc., etc.? Oh, I didn't realize that that was important. I said, well, it's very important. We are more concerned about reproductive organs, but we're just as concerned about thyroids and many other, all the parts of your body. And you need to, by law, have to wear a shield, and we don't treat patients without the appropriate radiographs. He said, oh, well then put it on. Well, the guy was being a fool. He really was being foolish, and I think he was playing with her. This was a young, very pretty young lady, and he thought he was being cute. He wasn't being cute, he was being stupid. And from that point forward. But again, it is more than important. It is against the law to take x-rays without a lead shield. Now, there are some lead shields without collars, without thyroid collars, because we're taking like the panoramic picture and some of the external pictures. But in general, every patient must wear a lead shield covering the majority of their body that's exposed to protect all of the tissues in their body. This shows the young woman covering the patient with the collar. Film, as we said, comes in different speeds. The size of the silver bromide crystals is the main factor in determining the film speed for film, dental film that is used. All film, whether it's photographic, which almost no one uses anymore, or a dental radiographic, is covered with 3 silvers: silver bromide, silver halide, and silver iodide. The silver bromide crystals, the size of that crystal determines the speed of the film. And we want to use the fastest film possible. Okay? A fast film requires less exposure, and it is a simple, and fast speed film is the single most effective way of reducing the patient's exposure. Fast speed film is available both for intraoral pictures, which you're going to learn to take, and extraoral, which are more like the panoramic. Okay? Film holding devices. The use of film holding devices keep the patient's hands and fingers from being exposed to X-radiation and minimizes their exposure. Film holders will also hold the film in a stable position and aid the operator in properly positioning the film. You will be learning as the coming days come using, we call the XCP film holding device, which has been around for the last 25, 30 years or so, but before that, we were eyeballing the cone of the X-ray, hoping to be able to hit the film at the proper angulation. Today, using the XCP, your first set of films that you take will be probably very adequate films, whereas not using film holders, it takes many, many sets of film before you even get close to being competent. So it is no longer acceptable to take X-ray pictures of human beings without film holding devices. This shows a human being. In the days when I was in dental school, the doctor or the technician didn't hold the film for the patient, which they did prior to this, but the patient held the film with his or her finger. And you can see the exposure area that this patient has been exposed to, as opposed to the amount of the space of an X-ray film using the film holder, the XCP. And so this is no longer an acceptable way to take pictures. Yet that's the way I was taught in school, and until the XCPs came along in roughly 1975, 1978, this was the way we took the pictures. It is no longer acceptable ever to do that. Okay? Using the proper exposure factors also limits the amount of X-ray exposure to the patient, obviously. We adjust the kilovoltage. Remember we talked the kVp. We adjust the milliamperage for density, and we adjust the time to control the exposure factors. A setting of 70 to 90 keeps the patient exposure to a minimum, and 70 is always preferable. On some dental units, the kVp are prescribed by the manufacturer, and you can't change it. And on most modern X-ray machines, this is all being done by a computer inside the machine. Proper techniques are necessary to ensure the diagnostic quality of films and reduce the exposure, the amount of exposure to a patient. Films that are not diagnostic or non-diagnostic must be retaken. This results in additional radiation exposure to the patient. So when the doctor looks at an X-ray and says, Janie, take this over again, Even though you've been very careful, but you didn't get all of the angulation or the end of the root or whatever the doctor is looking for, consider that this doctor is an appropriate doctor and one you should emulate. Don't think of him or her as being a pain in the butt because he's making you take a picture over. Because if we needed to take the x-ray, we need it to be good enough to diagnose why we exposed the patient to start with. And so retakes are very, very important. Retakes are a major cause of unnecessary radiation to patients and must be avoided. And so you want to be as careful as you can possibly be. And sometimes, even being careful, the picture may not be as good as the doctor wants, and he may want you to change the angulation slightly. X-rays during pregnancy. The guideline for prescribing dental x-rays issued by the American Dental Association in conjunction with the Food and Drug Administration state that dental radiographic procedures do not need to be altered because of pregnancy. When a lead apron is used during dental radiographic procedures, the amount of radiation received in the pelvic region is nearly zero. What's the important word there? Nearly. Nearly zero is not zero, okay? There is no detectable exposure to the embryo or fetus with the use of a lead apron. What's the important word there? Detectable. The fact that we couldn't detect it doesn't mean 100% that it wasn't there. So we want to minimize the amount of radiation to pregnant women, even though the FDA and the ADA say it's perfectly fine. So how many of you think we should take an x-ray of a pregnant woman? Nobody? Well, the answer is yes and no. Now, you've all agreed that taking x-rays of a pregnant woman is probably not appropriate. Well, the answer is sometimes yes and sometimes no. And what do I mean by that? Young woman becomes pregnant, she goes off to her doctor to verify the test that you took at home, and the obstetrician puts you on prenatal vitamins. He says you've had your last cigarette, you've had your last alcoholic drink, you should probably eliminate certain things like too much tuna fish out of a can because of mercury and etc. And there are a whole bunch of things that are prescribed by the obstetrician when you're pregnant, okay? A good obstetrician will also say to you, go and have a good dental examination. Now, why does he say that, or why should he say that? Well, we know today that what is the most common cause or common effect in the human body of chronic infection? Where in the whole body is there the most amount of chronic and sometimes acute infection?
No.
The mouth. There's infection going on in the mouth in all of us to a certain degree. You have some cavities. You have a gum abscess. You have a swollen gum. You have all kinds of things that go into the normal process. So in the human body, the most common occurrence of chronic infection is in the mouth. The head and neck and the mouth, okay? So research and many sophisticated studies have shown that women who go through the pregnancy process, who have chronic infection in their body, no matter where it is, whether it's their mouth or somewhere else, those women deliver babies whose birth weights are statistically lower than would have been expected. We also find that the term of the pregnancy is also generally changed by having chronic infection in your body. The term of your pregnancy will not be as long if you have chronic infection in your body. So where is the area of the body that's most prone to infection and that we can detect without going into incredibly difficult testing? The mouth. So an obstetrician should send you to your local dentist for a good checkup. So if you walk into my office and I examine you, you announce that you're pregnant, I will take a very good look at your teeth. We will clinically examine your teeth, etc. If I see nothing of any concern, there seems to be no infection. There seems to be no cavities or decay that I can see. There seems to be no gum problems, swellings, etc. In those cases, most dentists will defer and say, Mrs. Jones, come back in 9 months or 8 months, whenever the baby is born, and I'm going to take x-rays that I normally take at that time. Okay? Now, in the other case, when you come in, the woman comes in to see us, and the doctor looks in the mouth and sees an old restoration, silver, gold, composite, it doesn't matter what it is, and it's not bothering you. You're not aware that it has a crack, or it's leaking around the margins, or there's something going on that's not right. In that case, we are going to take an x-ray of that particular tooth. We're not going to take 18 pictures. We're only going to take the ones that we have some semblance of concern. Because the worst thing that can happen to you, and we see it all the time in dental offices, women come in who have not had a dental checkup in a long time, etc., and your body's changed dramatically during the pregnancy period. Many women develop pregnancy gingivitis or inflammation of their gums. Many people develop cavities because their eating habits and their cleaning habits, etc., are changed. And the worst thing that can happen to you is to develop an active infection in your body, in your mouth, anywhere, but certainly in the body, in the mouth is where we look, and had those bacteria floating through the bloodstream, going down through the lymphatics, and crossing over the placental barrier. Those bacteria cross right over, and they swim with your baby. That's a terrible description, but that's what happens. And so, infection in the mouth where we can see it and we can diagnose it pretty closely without having to open up the rest of the body, etc., is very important that it be screened. And so many women who come into a dental office will receive no x-rays at that point, but many others will. If we see something that we can verify, that you're going to be safe for the 6 to 9 months. And almost every day, this is a very large office, but we get people in here almost every day, women who come in with a toothache, or come in with a swollen face or a swollen gum, and they've not been attended to during this pregnancy period. And that is putting you and your baby at some risk. So, now what do you think the answer is? Yes and no. Operator protection. A dental assistant who fails to follow the rules of radiation protection may suffer the results of chronic radiation exposure. Okay? But following these following rules, dental personnel can keep their radiation exposure to 0. Rules for operating protection: never stand in the direct line of the primary beam. Remember I said this electromagnetic wave goes in a straight line. It doesn't go around corners, it doesn't bounce off of things, etc. So you never want to be in the straight line. Always stand behind a lead barrier if one is available, or a proper thickness of drywall. Now, in most dental offices today, we don't have to use lead barriers because we can arrange it such that the tube head is at least 6 to 9 feet away from exposing anyone else. Now, in medical facilities, if you were going to a hospital or to one of the radiograph, many times you'll see the operator who's taking an x-ray of your chest or a broken bone will have to jump behind a wall with a leaded glass window. And that's because the medical x-rays are much stronger and they go much further than 6 to 9 feet. And the operator can't get that far away. So they have to stand behind a pillar which is lead lined and leaded glass so that they can operate on the patient. But in dentistry, most cases this is not necessary. Every once in a while we design an office and someone may be on the other side of the wall that could be exposed, and in that case we need to lead line that wall. Years ago when I opened my first practice, all of my walls at that time in 1969 had to be covered with lead. And that was an enormous expense at that time that isn't really necessary in most cases today. Okay? If a lead barrier is not available, stand at right angles to the beam. Never stand closer than 6 feet to the x-ray unit during an exposure unless you are behind the barrier. Okay? Now, we talk about the 3 types of monitoring devices used to determine the amount of radiation exposure to personnel. The first and most popular is the film badge. The second is the pocket dosimeter, and the third is the thermoluminescent thing. But in almost all of medicine and dentistry, the most popular is called the film badge. Okay? And film badges are supplied to dental personnel by their doctors. The ruling on how long you have to wear a badge varies from state to state as to whether it needs to be worn all the time or it can be worn part of the time. In the state of Maryland, for example, if we put a new machine in operation in this office, we must have the personnel wear a film badge for several months after the installation of a new machine to make sure that there's no stray radiation. After that period of time, we can withdraw the badge, or we can leave it in place. If your doctor gives you the badge to wear, you should cherish it, you should wear it, and you should appreciate that he or she has given it to you. Okay? It is not very expensive to provide, and many offices don't provide it when it's absolutely called for by the law, for really one reason, and that's the abuse of the badge. If you don't wear the badge every day when you're in the dental office, then wearing it Monday and then forgetting about it Tuesday and Wednesday and putting it on Thursday has no value because it's not really measuring the whole time you're potentially exposed. The other problem is that sometimes we even find people will pick up somebody else's badge. They're on a block in the break room, and people will pick one up and put somebody else's on. That also does no value to you or to the office. And thirdly, probably most importantly reason, is that these badges are dumb badges. They don't know radiation from the sun, from radiation from the x-ray machine. It only picks up radiation exposure. And so if you wear your x-ray badge and you go outside and have lunch every day in the spring and the summer wearing your badge, that badge can come back as positive exposure because of the radiation from the sun. Now, if your badge individually comes back as positive, and we send it in every 30 days, and it comes back as positive, then if you're the only person who's came back positive, you cannot take x-rays again until the owner doctor determines and writes a report as to why you were positive and no one else was. There's something you did or didn't do that puts you at exposure, etc. If many of you come back with a positive reading, then the office cannot take x-rays, and that shuts us down. And so it is very important if your doctor gives you the badge to wear on a regular basis, then respect it, wear it, and thank him. And if it's not out there, it's not because of money, because the cost of these badges is very nominal. It's because of the possibility of its being abused. Anybody question about that? Did I answer your question okay? Good. All right. Equipment monitoring. Dental x-ray machines must be monitored for leakage radiation. Every state has a period of time where they will come and test the x-ray machines in the office. In the state of Maryland, they come roughly every year, sometimes a little bit longer than that, but they will come and test each machine to make sure that the tube head is not leaking radiation, and that the tube is, with the settings that we put in it, is accurately putting out the radiation that we think it is. And so periodically, x-ray machines in every medical and dental office have to be checked and recertified by the state radiation committee. Dental x-ray can be monitored through the use of a film device that can be obtained from the manufacturer, but that doesn't hold up for the state. They want to come and test these machines. And what we do in our group is that we send a letter to them, a certified letter, when we know that our year or so has gone by, telling them that we want to be tested. So that we put them on on alert that we want to be tested. And indeed, in addition to the state monitors, we bring in the dental supply people who supply all of our equipment, and we have them test our machines and the area around it on a regular basis, especially when we put newer machines in place. Okay? Now, if the patient is a child and cannot cooperate, the child may be seated in mom's lap. Okay? Now, in this case, the child is a young child and we needed to take x-rays for some reason. Generally, we don't take too many x-rays under the age of 5 or 6, but at the age of 6, we like to take what's called the panoramic, which shows all the developing teeth of the patient, tells me if there's anything missing, anything extra, any impactions, all kinds of things that can be determined of a child in the transition from baby teeth up to the age of 6 into the transition of what we call the mixed dentition from 6 going all the way up to 18. And so this little boy came in and he was not very cooperative, but I saw something that, even though he was under the age of 6, that concerned me. He might have had cavities, he might have had an infection, he might have fallen down and broken a tooth or whatever, but in this case he was under 6 and we needed to take an x-ray. Mom in this case was perfectly fine, she was not pregnant. So mom can sit in the chair and hold the child, as well as dad, with their own lead apron. The child gets one and the mom gets one. But it is against the law for mom to hold the child if she is pregnant, regardless of the number of lead shields she wears, because mom is getting no advantage of the radiation herself. So if she is pregnant, she cannot hold the child. And many moms will say, it's okay, I don't mind. Well, you mind, etc. We cannot do that. And so when little Stinky comes in and he won't sit still, what we'll do, if he's not in pain, it's not bleeding, etc., he has cavities or a problem, we'll tell mom to go home, bring daddy back, bring grandma, bring somebody who's willing as an adult to act as the surrogate parent to that child. Now, unfortunately, many times, as a pediatric dentist, we saw many, many traumatic injuries, kids falling off of trikes, coming in with abscessed teeth, and mom, it seemed invariably that when little Stinky wouldn't sit still, his mom was pregnant. I think there's a direct correlation or indirect correlation between that. But anyway, the child comes into the office and he or she will not sit still by herself or himself, and mom is pregnant. And what do we do if this kid has a toothache or the child has broken a tooth? You as dental personnel should never ever sit as surrogates parents to this child. You do not sit in the chair and hold a child that doesn't belong to you. Is everyone clear about that? Sometimes I've had dental assistants say, oh, it's only one x-ray, I don't mind. But the fact is you should never volunteer, and if the doctor asks you to do so, you politely decline. It is way above your pay station. Okay? Now, what would happen if a patient came in and we needed to take an x-ray? Well, two things could happen. Number one, we could send this child to the hospital where it could be sedated and the x-rays taken at the dental clinic in the hospital. And on the other hand, as a pediatric dentist, I infrequently, but would occasionally, sit and hold that child myself. Now, I had a lead apron that was made for me. It covered the front and the back and my thyroid. And I also had a glove that was impregnated with lead. It was a white glove that was impregnated with lead, so that I minimized any radiation exposure to me. Was I happy about doing that? Absolutely not. But sometimes the kid is in pain and I can't be sending them to the hospital, and I would expose myself. But you as dental auxiliaries should never ever take that responsibility and accept it or volunteer for it. Is that clear with everybody? Good. Okay, now to end up our evening, there's a concept called ALARA. The ALARA concept states that all exposure to radiation must be kept to a minimum or as low as reasonably achievable, ALARA. And what that means is every possible method of reducing exposure to the radiation should be used to minimize the risk to the patient. The radiation protection measures detailed in this chapter should be used to minimize patient. Now, what this really means is that if you need to take multiple x-rays, you should take them. But you don't take any more than you need, nor do you take any less. So, for example, if I fell down and I hurt my wrist, the orthopedist brought me in and took x-rays. If he needed 4 exposures of my wrist to make a diagnosis, he should take 4 x-rays. He shouldn't take 6 or 8 because he doesn't need it to make the diagnosis. But nor should he take 2 x-rays if he couldn't make a clear definition or diagnosis. He did me no favor by limiting the radiation if he couldn't make the diagnosis clearly. So you take every x-ray you need, none too many and none too few. And that's the mantra of radiation, both in medicine and dentistry, is called ALARA, A-L-A-R-A.